In this unit, we're going to focus on looking at conformers. Conformers are defined as different three-dimensional shapes of a molecule that result from rotating around carbon-carbon single bonds. So this would be a great time to get out your molecular model kit and construct ethane, a 2-carbon alkane, where the black atoms are your carbon atoms connected by a single bond here, and then in white we have our hydrogen atoms, and you can just kind of ignore that red that I've added there for emphasis of that particular hydrogen atom. So when we talk about conformers, we can illustrate this using our molecular model by rotating around the carbon-carbon bond. And we can see that by rotating around that carbon-carbon bond, what I'm doing is just holding this black atom on the left constant, steady, and rotating around that bond, moving as a result the 3 bonds to hydrogen on the right, rotating this carbon around, and that results in creation of an infinite number of different conformers as we go through the full 360-degree range of motion there to rotate all the way around to ultimately get back to the original conformation that we started with. We can also look at this viewing down the carbon-carbon bond so that our carbons are stacked, so that this carbon in front is shown directly in front of the carbon that's in back there, so you can't even see the carbon in back. And we can rotate through, rotating either of the 2 sets of atoms that are bonded to either of the 2 carbons, holding the other one steady, much like rotating the prop of a plane. We can rotate around to create all the different possible conformers of this molecule. This is a special feature that is in place for carbon-carbon single bonds at these sp3 carbons here. It is a phenomenon that sp2 carbons and sp carbons can't undergo. If we build a molecular model of ethene, a 2-carbon alkene, and we try to rotate around that carbon-carbon bond, you're going to find that it's very, very, very difficult to rotate around that carbon-carbon bond in the molecular model. The same is true in real life, in the real actual molecules, in that you can't rotate around these carbon-carbon bonds that are double bonds or triple bonds. Instead, those are considered to be essentially locked into place. It takes so much energy to rotate around these bonds that for all intents and purposes that process is not relevant. So what we're going to focus on when we look at conformations is rotation around carbon-carbon single bonds. We're going to start by looking at the example of ethane and other alkanes that are acyclic, meaning they don't have any rings, and then later on in units toward the end of the chapter, we're going to be looking at conformations of cyclic alkanes, particularly looking at cyclohexane. So we're going to start with ethane as our model here. Keep in mind that the bond angles around each carbon atom are not changing as we rotate around to these different conformers, just rotating around the bonds. We're not changing any bond angles. The bond angles at each of these 2 carbons are still the ideal 109.5 degrees for an sp3 carbon. When we look at the different conformers that are possible here, we have special names that we can ascribe to a couple of those conformers. One of those conformers that's worth noting is the so-called eclipsed conformer. The eclipsed conformer is one where the groups that are bonded to the 2 carbon atoms are eclipsed. So what I've created right here is the eclipsed conformer, and if I hold this just right, you can't even see those hydrogen atoms that are in back there because they are eclipsed by the ones that are in front. What this means is that there is a dihedral angle of 0 degrees separating the white atom in front here from the one in back. Those 2 hydrogens are separated by a 0-degree dihedral angle. If we start to rotate around the carbon-carbon bond, we start to create a larger and larger dihedral angle separating the hydrogen in back from the one in front, forming this dihedral angle. And we eventually rotate around enough to get to the so-called staggered conformation. The staggered conformation is the one where those atoms are spread as far apart as possible. So we've totally staggered the bond to here, which goes to the carbon atom in back, with the one to here, which goes to the carbon atom in front. So if you look at the molecule straight on, like this, you can see that all of the bonds are staggered as far apart from one another as possible. And this is the lowest energy conformation. So the eclipsed conformation is where all of the bonds and atoms are eclipsed, overlapping in other words, fully. The staggered conformation refers to the situation where the bonds and atoms are going to be separated as far apart as possible. And when we say they're separated as far apart as possible, we're still keeping within the constraints of keeping the ideal 109.5 degree bond angle, etc. So what you see here is a staggered conformation of ethane. When we're looking at these molecules and going through, we can also look at more complex molecules such as butane and look at the conformations of butane as well. So what we'll do now is construct a molecular model of a 4-carbon chain, such as would be the case with butane, and we'll focus on a couple of different bonds within that molecule. I've created the 4-carbon butane chain here. In this 4-carbon butane chain, we can rotate around any of the carbon-carbon bonds that we want. So we can rotate around this carbon-carbon bond, this set of carbons, or this set of carbons. And if we're talking about what conformer we're going to be defining, we generally have to specify which carbon-carbon bond we're rotating around. For example, we're rotating the bond between carbon 1 and carbon 2, between carbon 2 and carbon 3, or between carbon 3 and carbon 4. So we have to set up a frame of reference. So we could set up our frame of reference here as looking down the bond between carbon 2 and carbon 3. So the bond between carbon 2 and carbon 3 would be right here, C2 and C3. And we're going to create the different conformers that correspond to that. So we can hold that bond there in place, and we can rotate around it by rotating like the prop of a plane, the group here in front. So we're rotating around this carbon-carbon bond right here to rotate. As we rotate, those groups have to move around. And so we're going to create, this would be an example of an eclipsed conformation. So you can see that these two groups are eclipsed. This hydrogen atom in back is eclipsed with the methyl group in front. Hydrogen atom here is eclipsed with the methyl group in back. So this is an example of an eclipsed conformation. We can continue rotating around our carbon-carbon bond here to get to the group that is staggered, as an example here. Continue rotating around to get to another eclipsed conformation, rotate around to get to another staggered conformation, rotate around to get to another eclipsed conformation. I want to bring this eclipsed conformation to your notice because this is going to be absolutely the highest energy conformation that this molecule can possibly adopt because of the fact that the two methyl groups on the end are as close in space as they could possibly be by rotating around carbon-carbon bonds. And when they're this close in space, they undergo a lot of torsional strain. Torsional strain is what results from the atoms and bonds being too close in space, and these are particularly too close in space. We also describe this crowding as steric hindrance, where these groups, the methyl groups, you can see them clashing together. They are definitely too close in space. That makes this conformation unfavorable, high in energy because of the atomic crowding and the eclipsing of these electrons in the bonds, which would prefer to be further away from one another. So as we shift away from that eclipsed conformation with the two methyl groups totally overlapping, we go down and down in energy, getting to a relatively energy minima here, and then continuing onward up in energy to the next eclipsed conformation because, again, the too much electron overlap, too much atomic crowding, going down in energy to get to the staggered conformation here. And in this particular staggered conformation, this staggered conformation is absolutely the lowest in energy because it's going to put the methyl group that's back here 180 degrees away from the one that's up here. So it's spreading those apart as far as they possibly can be from one another. So we've taken relative to this C2 to C3 bond, the methyl group here is as far away as it can be from the one up here, or in other words, it's staggered. We can continue rotating to get to additional eclipsed conformations and additional staggered conformations, making it all the way around back to our original eclipsed conformation, which was our highest energy conformation. What we're going to do in the next unit is look at how we can go about drawing these different conformers on paper and what additional terminology we need to go along with these descriptions of staggered versus eclipsed, and are there further descriptors that we can use to describe what's going on as we rotate around these carbon-carbon bonds. So that's what we'll be doing in the next unit.